Okay, welcome back. This is now section 2.2, and it's on conditional statements. Okay. These are very prevalent in your math books. They're statements that begin if this, then that. Okay, that's exactly what we're talking about. And yeah, they're really all over the place. There are some things we have to be careful about, and I don't know. Anyways, we'll start with the truth table. The symbol we use is this arrow symbol. So if P, then Q. So when we symbolize everything, we'll kind of get rid of the if part of it. So I don't know, maybe I should have written if P, then Q, right? So writing this in symbols, we'll write P, then Q. If P, then Q. Great. So let's first look at the truth table for it. Get the truth value. So again, start with P and Q here, and true, true, false, false, and true, false, true, false. Okay. So the way the book wants you to think of this is you can kind of, they have these statements that kind of, I don't know, it's not necessary that you would rote memorize these tables. Okay, I hope that's not what you're thinking. Sort of the helper statement here, if you show up to work, then you will get the job. And you could make up your own helper statement, like if you hit the ball out of the ballpark, then you get a home run. Something like that, right? In this case, and what the book is having you do is think this is your employer talking to you, okay? And your employer tells you if you show up for work, then you're going to get the job, the easiest job in the universe. So when would that employer be lying to you? Okay? And you think of that in order to fill out the truth table and get the truth value. So if you show up to work and then you get the job, he's definitely told the truth there, right? So you can say that would be true. Let's say you showed up to work, but then he didn't give you the job. And you're thinking, well, hey, he said if you showed up to work, you're going to get the job. Oh, he's lying to me. Okay, so that would be the case where it's false. These other two cases are kind of true, but not in just in the fact that he didn't lie to you. It doesn't line up to the statement, certainly. For in the first instance, you're not actually going to work, but the guy gives you a job anyways. But technically, he hasn't lied to you, right? So you would consider that true. And likewise here, you didn't show up to work and then you didn't get the job. So no, he's not lying to you. So you write true there. All right, so I mean, you can like rote memorize the truth value, but it's better to kind of start thinking in like these example type ways. Okay. One important operation we need to do to implications for these conditional statements is negation. In order to pull off a negation, we're going to have to use De Morgan's. And in order to use De Morgan's, we're going to have to translate this conditional statement into an OR statement. Okay, so section 2, some logical equivalences. If P, then Q is logically equivalent to, believe it or not P or Q. And we could think of one of these kind of real life, I don't know, thingamajigs to get us there, right? So in this case, we're going to say if you don't get the work on time, then you're fired. So if you don't get the work on time, then you're fired. And the logical equivalent statement is either you get to work on time or you're fired. So the negation of not getting the work on time would be saying you get the work on time. So either you get the work on time or you're fired. And hopefully you can appreciate the fact that those two kinds of statements are exactly the same. So this is either you get to work on time or you're fired. Okay, so it's not at all, at least symbolically, intuitive. But if you can remember these kinds of statements, then you're going to be able to remember how they go from here to here, and then hopefully remember how to negate conditional, which will result in via De Morgan's conjunction, right? Okay. So, anyways, let's then talk about the negation of a conditional. So, section 3, negate conditional, and we will be doing this later on in a more complicated context. But for right now, let's take a look. So the negation of if P then Q. So we can replace P, if P then Q with not P or Q. So again, if you don't get the work on time, then you're fired. So either you get the work on time or you're fired. Okay, and we're just carrying over the negation symbol. Then we can use De Morgan's rule, or De Morgan's law, to kind of, and I don't want to say distribute, right? Because we have, that means something else in this context, but use De Morgan's and you get a not P, which is the same as P. It's a double negative law, and then and not Q. Okay. So the negation of a conditional results in a conjunction. Okay, so very important. I'm sort of blowing through it, but this isn't going to be one of those ones where, hey, here it is, we're never going to use it again. No, I don't want to lead you down that road. This is something that's important. Yes, we are going to use it again. Okay. All right. Now we want to look at contrapositives. And the contrapositive does come up if you've taken calculus. You probably remember seeing that once or twice. If a function is how does it go? If it's differentiable, then it's continuous, right? If it's not continuous, then it's not differentiable. That would be a contrapositive. So you negate both sides and reverse the direction of the implication. So what? Basically, if P then Q is logically equivalent to negate this guy, so you have not Q, then negate this guy, not P. Okay? And they'll put you through a bunch of problems so that a calculus type problem, I guess I'll go ahead and do that again. If a function is differentiable, then it's continuous. Okay, and so the power of logic in this context is that it gives you a whole new theorem to play around with, right? So I can go from this theorem to the theorem that says if a function is not continuous, then it's not differentiable. And you could think through other math examples. For instance, if a number is even, we'll say one of the counting numbers, if a counting number is even, then what? It's divisible by 2, right? Then it is evenly divisible by 2. I'll just say it is divisible by 2. I don't think calculus is a prerequisite for this class. So don't worry if you're like, what is he talking about? That's okay. So if a counting number is even, then it is divisible by 2. So the contrapositive of that statement, which is logically equivalent, would say if a number is not divisible by 2, a counting number is not divisible by 2, then it is not even. Okay. Okay, so you know, in math, it's a nice way to produce another theorem that you could use if you maybe know something about whether it's divisible, but maybe don't know what if it's even or odd or something. I don't know, something like that. Anyways, naturally, students will look at this and then start saying, well, can I say if P then Q is, can I say that's equivalent to if Q then P? And then there's other ideas. Maybe I could say that not P implies not Q, right? Maybe that's equivalent as well. And it turns out not all the time, right? So sometimes it'll work, you get away with it, but usually there's going to be exceptions. You can see that in the truth tables, right? So those cases are called the inverse error and the converse error. Okay, so let's take a look-see at that. 5 converse / inverse errors. The following are not logically equivalent to if P then Q. So we'll say if P then Q is not logically equivalent to if Q then P. Okay, and then this is called the converse error. Likewise, if P then Q is not going to be logically equivalent to not P, then not Q. So just negating both sides, that's called the inverse error. Or just call it, let's just call it the inverse. Okay, okay. So let's look at, I don't know, let's look at number 22 from the book. Maybe I get another example. It doesn't seem I have any of the comment. Oh, here's one. Okay, so find the converse and the inverse. This is number 23, rather. So you can see it. That's number 23. It used to be 23. It's probably changed, but they want you to find the converse and the inverse. The one example I always use with my calc students is if you hit the ball out of the ballpark, then you got a home run. The converse of that would be if you got a home run, then you hit the ball out of the ballpark. And those aren't the same things, right? You can still get a home run without hitting the ball out of the ballpark. You can get it in the park home run. Okay, so they're not logically equivalent, and that's the one example I keep in my head to kind of remember it, at least for the converse. Okay, so anyways, there's 23. Let's find the converse and the inverse. The original statement, I'm not sure what the heck it was. We'll say, crap, gotta look it up. Sorry, don't have it written down. 2.2. Okay, I got it. Just over here. One cool thing about watching videos is you might have like one of those ×2 buttons, so you can always listen to or watch the video twice as fast as normal. If I don't know if YouTube has that feature, but I use it whenever I'm forced to watch other people's videos. I just hit the ×2 and it goes faster. Anyways, number 23. Let's take a look here. They want the converse and inverse of the ones in number 20. So part A, if P is a square, then P is a rectangle. Okay, they also kind of in the homework in the software they'll ask you sometimes, is this true or false? So you can compare and contrast. This case is true. Squares are rectangles. Okay, all squares are rectangles. So anyways, let's find, well, let's do the contrapositive too while we're here, right? So for the contrapositive, it'll just be, so the contrapositive, rather than writing contrapositive, I'll just write, this is if P then Q, so the contrapositive, not Q, if not Q then not P, right? So I'll have if P is not a rectangle, then P is not a square. And that's true. Okay. So this one was true. This one's also true. If you're not sure about geometry stuff, there's Google. Go on Google and figure it out. Okay, so that's the contrapositive. The converse statement then, if Q then P, would be if P is a rectangle, then P is a square. Okay, that's definitely not true, right? Because there's cases of rectangles where the sides are, the base is a different length than the height, right? And that wouldn't be a square, but it is a rectangle. So this is patently false. And then the inverse, okay? So that would be not P implies not Q. So in that case, I'd be saying if P is not a square, then P is not a rectangle. And again, in this case, that's not true. Because you can have objects that are not squares that are, in fact, rectangles. A square is something where all of its sides are the same length. Okay. Okay. So hopefully that helps a little. Okay. If and only ifs, and then we want sufficient and necessary condition problems. So first off, if and only if. And there's also only if cases. Only if, and then if and only if. And the way I kind of think of the if and only if, it's an implication in both directions. Okay, the if part is an implication in this direction, and then the only if part is an implication in this direction. So I don't know if my if an animal has fur, then it's my cat. Okay, you could rewrite a statement like that as an animal has fur only if it's a cat. Okay? So that would be that forward direction when you have these only ifs, but when it's plugged into the middle of your statements. Okay? So if I hit the ball out of the ballpark, I get a home run. You could also say that hitting the ball out of crap. Okay, so it's a little confusing. Okay, so let me do the truth table, and hopefully that'll kind of clear it up. Okay, so part A, P only if Q. Okay, so what I'm saying is this case here is equivalent to it's equivalent to P then Q. Okay, so in our symbol notation, P then Q. Just another way of saying that. It's almost annoying. Let's just keep everything consistent and just say if P then Q. But let's look at the truth table. P Q. True, true, false, false. True, false, true, false. And then P only if Q happens. So you're only going to have P happening if Q happens, right? So here, Q happens and you get P happens. So that's not lying to anyone. Here, Q doesn't happen, and then P happens. So that's kind of you're lying, right? That's the case where you're lying. Here, P only if so Q happened, but it doesn't necessarily mean that P has to happen as well. P will only be there if Q is there. Let's kind of think of it that way. So in this case, it is kind of true. Okay? P isn't there, but that doesn't. This statement doesn't say that it has to be there. It's just it's only going to be there if Q is there. And then finally, Q is not there, so certainly P is not going to be there. That's a true statement. So if you remember the truth table for if P then Q, that's exactly the same thing. Okay? So again, when you see this P only if Q, you basically just think of that as if P then Q. Okay? Okay, and then if you have P if Q, that's the reverse direction. All right. So let's look at that. I guess we call that part B. P if Q, you're going to say that's kind of logically, think of that as being the same thing as saying, and we don't ever do this, but we would have to write if Q then P, right? You may think of it in your brain as kind of the reverse direction of if P then Q is like this, and it's converse is basically what you're looking at. So P of Q is this. Okay, and then its truth table is just going to be the reverse, or rather, let's take a look at it really quick. P and Q, and P is true, true, false, false. Q is true, false, true, false. And you're just thinking of it in this direction. Okay, so if this is true, this better be true. So Q then P, or rather, if Q then P, P if Q is another way. Okay, so you start here, true, true, that's true. False, true, that's true. True, false, that's the only case where it's not true. So that's false, and then finally false, false, that's true. Okay, then we kind of smack these together. So P if and only if Q. Sorry, P if and only if Q. So P if Q, of course, is Q then P. Okay. And P only if Q is the same as P then Q. Okay. That English is so confusing. Wouldn't you just like to get rid of all of it and replace it with symbols? Well, I would. Anyways, let's look at the truth table for this case. And they're going to, instead of writing it like this, they're going to use the double-headed arrow, P if and only if Q. Let's look at the truth value for it. So we have P, Q, and then we have usually put the commutative law for the conjunction says we go P then Q, and Q then P is logically equivalent as well. So I'll just work with that. So we have P is true, true, false, false. Q is true, false, true, false. And then I'm going to go through and do the two sides first. So if P then Q will be true, false, true, true. If Q then P, I'm going in the other direction now. So true, true, false, true. True, false is the bad one. And then false, false is okay. Then I want the conjunction of these. So that'll be true only when both are true. So true, false, false, and then true. And that's the truth value. Okay. All right. More confusing stuff. The necessary and sufficient conditions are also ways of talking about if, also sort of different English forms of the conditional statements. Okay? Personally, I avoid them because it's just confusing, but they're in the homework. I just want you to be aware of them. But like I said, sometimes you'll get a teacher that talks in terms of necessary and sufficient conditions, and it's a good idea to at least have heard it here first, and then you could look it up if they ever try to pull that on you. But all right, I never use the things. So anyways, R is a sufficient condition for S. Is the first type here. So we'll go through the truth table and kind of figure out what it is. So true, true, false, false, true, false, true, false. So to say that R is a sufficient condition for S means that if R is there, then S is definitely going to be there. Otherwise, who knows, right? All right, so if R is there, then S is there. So R is here, and S is there, so that's definitely true. This time they're saying R is here, but then it turns out S isn't there. But R is a sufficient condition for S, so that can't be true, so you'd say false. Here R isn't there, but then S turns out to be there. Well, that's kind of true, you know, nobody's lying to you there. And here neither R or S is there. So that one is true as well. So what the heck is this thing? If you think of it in that sort of way, well, it's just an implication, right? It's just the same as saying if R, then S. Okay. Let's look at the necessary one. So saying R is a necessary condition. And you can almost guess what this one's going to be, right? It's going to be S, if S, then R. Let's go to kind of try to fumble our way through this. Okay, so true, true, false, false, true, false, true, false. Okay. So R is a necessary condition for S. If S is true, then R has to be true. Okay, so this first one is true. This one is also true. Okay. So here, it doesn't really mean that, you know, if S isn't there, you haven't violated anything. It's just a condition for S to be there that R is there. The next one, here, S is here, but then R isn't there. So that sort of is bad. Okay, so that's false. And then the last guy is going to end up being true. So again, what did I say? This is just the other version. This is if S, then R. Okay. And then if you put them together, R is necessary and sufficient condition. That's exactly the same as the if and only if. Okay, so if you say, lastly, then R is a necessary and sufficient condition for S. If R is a necessary and sufficient condition for S, that's equivalent to saying S if and only if R. Okay. Okay. So you know, like I said before, there's in English there's a lot of different ways to say the same thing, and that's kind of what they're getting at here. They're trying to get you to translate back and forth between English and sort of an algebraic system. Okay. Maybe let's look at some exercises then from the book with this necessary and sufficient conditions stuff going on. Let me find one. There's also R unless S is in the exercises. Okay, it's buried in there, but it does come up every once in a while. R unless S is the same as if not S, then R. Okay? So every once in a while that will come up. Store that in your memory banks. And let's look at number 32. Does that work? Oh yeah, okay. So here in number 32, we have an if and only if statement, and the book wants you to rewrite it as two if-then statements. Okay, and you'll see these problems in the homework as well online. Okay, so problem 32. It says the quadratic equation, this quadratic equation has two distinct real roots if, so this quadratic equation has two distinct real roots if it's discriminant, and we'll abbreviate discriminant with a delta symbol. If it's discriminant, sorry, it's an if and only if. So this quadratic equation has two distinct real roots if and only if its discriminant is greater than 0 and oh, here it is. And oh, that's it. Okay, so the quadratic equation has two distinct real roots if and only if its discriminant is greater than 0. Okay, so we need to rewrite this as two if-then statements. So the only if part is going in the forward direction. Okay, so the only if P, only if Q, we can write the quadratic, if the quadratic equation has two distinct roots, then its discriminant is greater than 0. Okay? And then the P, if Q is going in the other direction, that part of it, P if Q, or if you'd rather Q if Q then P, that's starting at the discriminant part and ending at the front, right? So if the discriminant is greater than 0, then the quadratic equation has two distinct real roots. Okay. So all you're doing is breaking the thing up into the forward implication and then the backwards implication. Let's do ones with the sufficient condition. Let me make sure I got the right problem number. All right, so I want to look at number 41, I believe, if I can find it. Of course I can't. These stupid page numbers are all screwed up. Oh, 3. This is 6, problem 65. 64. Okay, sorry. So problem 41. Okay. Rewrite the statements in if-then form. Okay. So 41, having two 45-degree angles is a sufficient condition for this triangle to be a right triangle. Okay, so sufficient condition. We kind of have to back engineer what direction of implication that is. So sufficient condition, it guarantees that the other guy is there. So you can't have false true, which means it's the reverse implication, right? This is the Q then P version, where it's the inverse of the statement that you see. Okay, so to rewrite it as an if-then statement, you would say if the triangle is a right triangle, then it has a 45 degree, it has two 45-degree angles. Okay? So if, or rather, did I screw that up? Sufficient condition, saying it's the reverse. Maybe I meant the four, oh my gosh, did I screw that up? Well, let's look in the notes, right? Oh, that's the forward implication, sorry. So R is a sufficient condition for us. That's if R then S. So we could just write it as is. If the triangle has two 45-degree angles, then the triangle is a right triangle. Okay, so be careful, look it up. I'm not going to put the necessary and sufficient condition problems on my test. So you won't have to worry about necessarily memorizing that. I personally don't have it memorized either, so I'm not going to beat you up about it. Let's look at one more, and then we'll call it quits. Problem 43. This time we want to use the contrapositive to rewrite the statement in if-then form in two different ways. Okay, so 43. These are in the homework, though, so you will have to do homework problems about these. Okay, so doing homework regularly is a necessary condition for Jim to pass the course. Okay, so first it's probably best to translate it into an if-then form, and then we'll find the contrapositive, right? Okay, so if this was the forward direction, sufficient is forward, necessary must be backwards, so we can rewrite this as if Jim passed, then he did his homework, right? Regularly. He did his homework regularly. Right? And then the contrapositive, we negate the statements and reverse the direction of the implications. So if he did not, if he didn't do homework regularly, then Jim did not pass. Okay. So again, the sufficient necessary condition stuff, it's kind of a headache, but it'll come up every once in a while. One thing that should be noted about theorems versus definitions in math literature, sometimes a sometimes a definition will be given kind of in this implication format, but that's not really what it is. It's not really an implication. It's just a definition. So definitions aren't really about logic per se. Okay, the logic comes in when you're proving theorems, and so maybe a theorem would be an if-then statement. Okay, but sometimes you'll see if in a definition, and they don't really mean if. Okay, so just be careful out there. Like I said, if you're really worried and you're going to go into pure math, then you want to probably take some sort of math logic class or something like that. It's more advanced than this. Okay, okay. I think that's it for this section. I'll see you next time.